So next up, we have Peter Gagarinov, who is a software architect with 18 years of software development experience, architecture, machine learning, applied mathematics modeling for finance and electricity markets. He's currently working on a system from machine learning to automate issue management in Jira, which sounds pretty useful, actually. Yeah, now he will talk to us about scalable machine learning with Apache Ignite, Python, and Julia. Welcome, Peter. Over to you.
Thank you. Let me share my screen really quickly. I'm going to talk about the backend for our product called Alliedium. And this backend uses scalable machine learning based on Apache Ignite, Python, and going forward, Julia. As was said, I'm a product manager and a software architect for this product. And the task this product is going to and is trying to perform is to simplify project management in Jira. It is designed as a plugin for Jira task tracking system, and it automates routine project management tasks such as ticket assignment, labeling, and ranking by priority. Those are just examples. We are constantly enhancing the coverage of what can be done via our tool. And to make this process seamless and automatic, we use machine learning by scanning existing Jira tickets and inferring statistical rules, statistical patterns by which we can automate those workflows. So the plan for today is to talk really briefly about Jira, then explain the task we have at hand for distributed machine learning backend, then describe the transition path from the legacy, our initial architecture, and to the most recent one based on Apache Ignite. Then I'll talk about the data migration tool we developed in-house called Apache Ignite Migration Tool. It's open source. And finally, I'll compare the machine learning libraries in Python, Julia, and Apache Ignite, and explain why we made the choices we made. So Jira is a very powerful platform which allows developers to build plugins called add-ons, and those add-ons are just integrate really nicely into the ecosystem, and they allow to utilize very convenient licensing model where plugin prices depend on the number of users, and this can be very profitable. And it's a large market because the number of users constantly grow around the globe. So having this task in mind, we formulated a list of requirements for our backend. Those requirements are pretty standard. What we wanted multi-tenancy, we wanted to use containers, microservices, we wanted scalability, we wanted backend distributed task queue. We wanted to be able to run multiple machine learning tasks in parallel and in a scalable manner. And we targeted both on-premises and cloud platforms because we have the clusters set up in-house. We wanted to support that for our internal needs. And Jira has a way to sell plugins for the variants of Jira called Jira Server that are installed on client premises. So this requirements was important. Those requirements for the backend projected quite naturally to the database requirements. So we wanted to have a distributed database, but still with support for SQL transactions, persistency, and in-memory storage. We wanted fault tolerancy, both horizontal and efficient, horizontally scalable and efficient, and most importantly, we wanted it to have a very good integration with Java. And the reason for that is because we had a sufficient number of high skilled developers in Java, and we wanted to build our technology stack on top of Spring Boot. We also wanted to have a distributed job queue inside database if possible. Automatic failover in case some nodes go offline. Our goal was to keep client data safe. That is why we wanted transparent data encryption. And naturally, we wanted to use container orchestration frameworks. We wanted to use them so that we can deploy in cloud very easily. So we decided to go with Kubernetes. And finally, we did not consider any commercial closed source solutions. And initially, we built a prototype using PostgreSQL database, Spring Boot, Hibernate ORM tool, and we decided to stick with Celery in a combination with RabbitMQ as a distributed task queue for running our machine learning tasks. And this choice was dictated by our good familiarity with Python ecosystem and namely scikit-learn library. And this library integrates quite nicely with Celery. But since then, within 1.5 years, we completely revamped our technology stack and switched to Apache Ignite. Unfortunately, Apache Ignite covered only maybe 85% of the functionality we needed. That is why we complemented it with technology built on top of Ray called RayServe. And what RayServe does, it provides a scalable cluster for serving machine learning models. And since then, we added deep learning models on top of classical machine learning models in scikit-learn, and that is why we switched to a combination of scikit-learn and PyTorch, not just scikit-learn. This is how our current architecture from the bird's height looks like. So basically, our system is in central place here. It's built as a combination of isolated containers. Each container is responsible for a specific task. Blue ones are Apache Ignite nodes. Obviously, we have web server nodes and load balancer that distributes requests from Jira Cloud among different nodes inside this Kubernetes cloud. And we have RayServe that is responsible for running machine learning tasks, but only those parts of machine learning that use classical machine learning. Deep learning is forward deep learning requests. Deep learning machine learning models require GPU, and that is why we run those inside Amazon Cloud using SageMaker. From our point of view, Jira instances are just multiple tenants, and users represent the physical users that communicate with Jira. So the reason we decided to switch from PostgreSQL is because PostgreSQL is not ideal database for our use case. It has strong sides. I'm sure that many of you are familiar with PostgreSQL and its nice features such as complete SQL support, transactions, and easy integration with Atlassian Connect Spring Boot library, that just an extension of Spring Boot, just a wrapper that allows to integrate nicely with GTPC databases. But it has its weak sides. So it's not scalable horizontally unless we use some kind of PostgreSQL-based distributed databases. And it requires a little bit more effort for mapping objects to table via ORM tools. Key value API is not native. There is no any built-in data encryption. There is only an official patch, and in-memory tables are not provided out of the box. They need to be approximated, but those approximations are not ideal. And then we evaluated a few options and decided to use Apache Ignite. It covered many use cases of ours. All of them are listed here. They are pretty standard. I'm sure that all of you are familiar with strong sides of Apache Ignite. I'm not going to talk too much about it. But the most important ones is that it has built-in data encryption, built-in transparent data encryption. And it has a very good integration with Java without having to use JDBC, which is quite inefficient, can be quite inefficient. And it has support for in-memory caches, which was very important for us. But when we started migration, we faced certain limitations. And the first thing we noticed is that there is no any provided by Apache Ignite, anyway provided by Apache Ignite to perform data migration and schema version tracking. And data backup restore functionality built into Apache Ignite has a few limitations, such as no support for encrypted caches, which very inconvenient for our case since we encrypt everything. Support for SQL is not complete. Transactions for SQL are still in beta, so they are not available in even in 2.10. It doesn't play very nicely with Spring Boot DevTools, but this can be worked around. It requires very careful network isolation when we developed on multiple workstations inside a single local network. And to work around that, we wrote a simple wrapper around IP tables and Docker configuration to make sure that it's very simple to configure a new workstation for a new developer so that it can run experiments both locally and inside Docker containers without disrupting activities of other developers. And this tool is open source. It's available at this link. I'm not going to talk too much about it, but you can click this link later and just investigate. A Python thin client doesn't support transactions, which is unfortunate because our machine learning runs inside Python, and we needed the most functionality out of Python API. And to be able to use that functionality, we had to use a Py4G Python Java bridge, which is a wrapper around Java API that allows to use the full functionality of Java API from Python. Those are the inconveniences. So to solve the first two problems, we decided to develop the data migration tool in-house. And right now I'm going to talk a little bit about it. So the tool is called Apache Ignite Migration Tool. It's open source. You can look at it at this repository at GitHub. So the way it works is different from the way the built-in snapshotting functionality for Apache Ignite works. So built-in functionality just takes a snapshot of on-disk data. This tool just extracts data from Apache Ignite cluster to a separate file system directory in form of other files. So as a result, this backup is completely isolated, it's separate from Apache Ignite cluster. Then you can run a few transformations on top of those other files to modify database structure and schema, so that the modified data can then be uploaded to the new Apache Ignite cluster. By new cluster, I mean the cluster that corresponds to the new version of the data with a changed schema, changed data structure. And it is usually the case when you make major updates to the product. And we did those upgrades a few times when we changed the list of columns inside our caches, which they changed the caches themselves. So all those transformations can now be clearly defined as set of patches, each patch incrementing the data version. And along with patching data, we can also patch metadata, as I mentioned. And those transformations are declared in a way that is independent on our format. So we have an internal Java API for defining patches, and those patches do not read data directly. They just receive data in nice format. Also, since data is completely separate from the cluster, you no longer need the cluster itself. So after taking the backup of the data, you can shut down the cluster or just interrupt the network connection channel between the tool and the cluster and just work directly on this data. And the backups created by the tool are made to be independent on the Apache Ignite version with a few exceptions, with an exception of query entity, cache configuration, and affinity key classes that are assumed to be stable. I know that in Apache Ignite 3, you are going to change XML configurations by replacing XML with something else. So in those cases, the backups won't be able to be read. But in other cases, if these class definitions do not change, which is true for, I hope, for upgrading, for instance, from 2.10 to 2.11, backups should be able to remain useful, should remain to be useful. We also support all the cache value types allowed in query entity. The full list is here, but basically all data types allowed for Apache Ignite SQL are supported. When it comes to cache keys, we support non-user defined Java types and affinity keys on them. Also, we do not require that topologies of source and target clusters are the same. So the source cluster can have 2 nodes, the target cluster can have 10 nodes. It doesn't matter. And we support encrypted caches. But it all comes at the cost of making certain assumptions. Firstly, we cannot load data from the cluster and then upload it back, but I think it's quite natural. Also, we assume that the target cluster and the source cluster both have access to user class definitions. By user classes, I mean the classes that correspond to cache values. So those classes can be different for source and target clusters, but they should be available beforehand. So the tool does not automate the process of transforming the class definitions. Class definitions should be available. Also, we only extract the fields that are declared inside query entities. So if some field is not listed in query entity, we do not back it up. It's just invisible to the tool. And we also back up in memory caches along with persistent caches. So having in memory caches does not mean that they are ignored. So now, once I shed some light on the tool, let us just go back a little bit and talk about replacing Celery with Apache Ignite. So when we transitioned from the old technology stack, legacy technology stack, to the new stack, we had to keep Python-based machine learning libraries. And Celery was very good in terms of integrating with those libraries. And Celery had a very good delivery guarantees for messages from the web server, from Jira to machine learning backend. But along with that, Celery had a few shortcomings. All of them are listed here. Basically, most of them are the result of Celery relying on RabbitMQ as a message broker, and integration with Kubernetes not being very, very good. So when we switched to Apache Ignite, we solved some of those problems. But along with solving some of those problems, by having native Java API for messages, having automatic connection failover, and potentially being able to use distributed machine learning libraries inside Apache Ignite, we introduced a few others. And those are weaker guarantees for delivery, because Apache Ignite does not guarantee that messages traveling inside Apache Ignite cluster are delivered. But for our case, it was not super important. Building machine learning libraries, Apache Ignite ML, lacks certain features for our case, and I'm going to talk about it in a bit. Python's client doesn't support messaging and computing API, but we wanted to use it. And because of that, we had to wrap Java API with Py4G, which I already mentioned, and it is Python Java bridge. So now let me explain why we could not use Apache Ignite machine learning and why we decided to stick with Python. So in our case, we deal with relatively small datasets, but we have a lot of model training requests. So the average dataset size is 10K records, and those requests are not distributed. So this data lies inside a single node. And here we compare the performance of just a couple of very simple models inside Apache Ignite machine learning framework, MLJ, which is a Julia-based machine learning library, and scikit-learn, which is Python-based machine learning library. As we can see, Apache Ignite works slower for our particular case because it wasn't designed for that. And we understand that it just not its use case. Then we had to choose between Julia and Python. Julia has its strong sides, flexibility, and easy parallelism, but for our case, it doesn't force it right now because of the few factors. I'm going to talk about it in a bit. You can see here that the performance is comparable. So for linear regression, scikit-learn is a little bit faster. For decision tree, Julia is a little bit faster. Also, we noticed that machine learning inside Apache Ignite has a limited number of solvers, and it did not allow us to compare head-to-head each of the machine learning algorithms in all three platforms. And most importantly, we noticed that Apache Ignite does not have support for nested cross validation and stratified cross validation. Both of those are available in both Julia and Python. So summarizing the differences between Python and Julia, and again, let me remind that we stopped considering machine learning inside Apache Ignite because it's slower performance for our use case. Then we decided to choose between the remaining two. And so where Python shines is integration with Apache Ignite because of having thin client. So being limited, it's still a very useful thing to have. There is no such thing for Julia. Also, we benefit a lot from having a framework called Reserve. Reserve solves the problem of serving machine learning models, many of them in a distributed manner. And in Julia ecosystem, there is a combination of Genie and Daga libraries, but those do not form an equivalent replacement, unfortunately, at least right now. Python has a much more mature machine learning ecosystem, and as we could see, in most cases, it performs a little bit faster or comparably fast to Julia. And the reason is because Julia ecosystem is not mature enough. But we still could use, if available, a richer API for Apache Ignite. Unfortunately, for Python, we have only thin client, but we have both Java API and C++ API with a functionality via a thick client. And potentially, we could wrap those, and we do so, for Python with Py4G. But in Julia, there is a library called Java call.gl, and we could wrap C++ API for Python via Cython, and in Julia via cxxwrap.gl. So in terms of being able to use the fully functional thick client API, those are equivalent. But where Julia is better than Python is easier parallelism, because in Julia it is possible to use native threads, while because of GIL, global interpreter lock in Python, we cannot use threads, we cannot use the full power of multi-core CPUs, and without spawning separate processes, which is less efficient for our case. And Julia is also more flexible because it's just a modern C++. You can write any custom code and it runs as fast as library code. So let me summarize the difficulties on our migration path from the legacy stack to the most current stack we have. So firstly, when we switched from PostgreSQL to Apache Ignite, we had to imitate the SQL table that was expected by Atlassian Connect Spring Boot library. In Apache Ignite, there are no native SQL tables as expected. There are only caches. So we had to use a trick and create this cache beforehand, and then Liquibase, which is a data migration tool and library used under the hood in Atlassian Connect Spring Boot, just noticed that cache, thought it was just an ordinary SQL table, and just proceeded with its execution. This way, we were able to trick this framework and use it without any changes. Also, we had a few fields, and still have, that are not of SQL data types supported by Apache Ignite, and we had to represent those as XML strings, and we had to use binarizable and query entity interfaces so that we can look at the values of those fields in tools such as the Beaver and DataGrip for debugging purposes. And we could not find any way to get a list of all available atomics inside the cluster. So inside our data migration tool, we just hard code those atomic names. There is just no any way around it. By replacing a combination of Celery, RabbitMQ with Apache Ignite, we also faced a couple of difficulties. Firstly, we could not use Apache Ignite alone. We had to keep machine learning libraries in Python, and we need to make those libraries, keep those libraries distributed. That is why we stick with a combination of Apache Ignite and Reserve. And we need to take an additional care on our front end in JavaScript to make sure that those weaker delivery guarantees of Apache Ignite do not make the user experience worse. And here is a layout of our backend architecture on a lower level. So basically here we delegate the classical machine learning tasks to Reserve and forward deep learning tasks to PyTorch using Amazon infrastructure. But inside Apache Ignite, we run the controller jobs. So the way it works, we spawn the machine learning controller jobs. It runs a job inside Reserve cluster. If it's classical machine learning, it stays here. If it's deep learning, it's forwarded here. That's all I was going to talk about. Any questions?
You took me by surprise there, Peter. Thank you for your talk. That was great. Good to hear of a genuine kind of machine learning case